Hello, everybody. So, kind of starting the restarting the recording. Had a guest come in, set up the from academic advisors, get everybody registered for the summer. We're getting very close to the end. With us taking 2 weeks on every module, we start module 7 out of 8 on Wednesday, or sorry, on Thursday, 2 days from today. But there's still an important issue from on the to-do list for module 6 to go over. We've been looking at lots of data structures and things like that. And we've seen about working with data, but one important thing we want to do with data is to put it in a specific order, sorting it, which has kind of become a noun in and of itself. And programming aspects, we refer to a sort almost as a noun when we talk about it. And this has been a big deal for, well, since the beginning of computers. Sorting the data has been a big deal because, yeah, it's very important. We need to sort and filter and all that stuff since the beginning of computers. So more than one generation of computer scientists has spent an entire working career developing and refining sorting algorithms, looking at some of the different ones. Some basic ideas, or there's a basic question we want to ask to begin with when we start sorting stuff. And that is, what is the order for our data? Because obviously there's going to be at least 2 main answers to that, categories of where our answer falls. So that's our topic for this evening, sorts. And yeah, the big question is, what is the order for our data? What is proper order for our data? And in general, there's 2 categories of answers, right? Every unique situation is going to have a unique answer, but we'll have basically 2 categories. 2 categories of answers, which would be a sequence. Oh, I should use types, because categories is one of the things I put on the list. 2 types of answers to that question, either a sequence or a category. Sequence, that's order or value, alphabetical order, increasing numerical order or decreasing numerical order, the things that the default .sort method on a list would do. Right? It puts it in order alphabetically or numerically, and either ascending or descending order, a few other options. Categorical sorts are a little bit more complicated because they will very much depend on the situation. Because, well, we need to know the details of the situation before we can even start to figure out what the categories are. So just they're just the general idea of it. So I wanted to look at a few different sorts. I picked 3 that are easy to work with, 3 that are easy to implement, and we kind of, I was thinking just set up a counter to see how many passes it takes to get our data sorted with the different algorithms. And yeah, then then 2 that are much better algorithms, but we'll just talk about them with the picture on the board, because they are quite a bit to get implemented. So the 3 that I had in mind are So our examples we're gonna do here in a second, we'll do a bubble sort. The big thing about this is it is probably the easiest to code up. And the idea is we do multiple passes through the loop in such a way that the small multiple passes to compare each element. So basically nested loops. The first loop walks all the way through the list or array, and then on each pass of the outer loop, the inner loop walks through the whole rest of the array to see if there's anything smaller or bigger. Because sometimes these are called sync sorts. Compare to each element and swap if necessary. Bubble, that term comes because from like, if we're looking at concerned with smaller, like increasing order, the ascending order, then the small elements bubble up to the top of the array. And if we want to go the other way, the descending order, the heavy elements or bigger things sink down to the thing, is where those names come from. I'll write this in all capital letters. Lots of overhead. So terribly inefficient, but the easiest one to code up. So if you have a small data set, it's where you're not worried about a few more passes through a loop, that's no problem. But you certainly want to use this a situation with millions of data points or something really, really big. The other one I was going to look at in our example is insertion sword. Go to a picture here. Yeah, this is scan through and look for something not in order and put it where it goes. Scan through. Looking for elements out of order. I'll make that plural because it's a machine. Obviously, we have to do that one at a time. Look for element out of order. Put it where it goes. So I drew a picture on this one. So we have this array or a list. What up here? 1, 3, 7, 5, 9. So that one's really close to in order, but that would be a nice easy start on it. So it's going to start here at our first element, and we'll look there. And then just kind of walk through and find something out of order. So it'll come over, look at the next element at 3. 1 comes after 3, that makes sense. So the loop's just going to continue on. A 7, okay, that makes sense. 1, 3, 7, stuff's increasing. But then when it gets over here, 5 would be smaller than a 7. So it's going to notice something's wrong. So it's going to take that and then come back to the beginning and do every comparison until it finds where it goes. So kind of walk through, look at every element one at a time, and then put it where it goes. zoom in on the board so y'all can see the stuff I'm writing here. The other one we're gonna look at this evening, these, I picked 3 that are really easy to implement. They don't take a lot of code. A selection sort is find smallest, put it in front, or at the beginning of the array, put it at beginning, and repeat until we've got everything in order. So it's a really big picture here. So 3, 12, 27, 2, 9, 21 is what I made up in my picture here. So this is gonna come through here. It starts with the assumption that our first element is gonna be the smallest one. So it looks there and calls that the minimum. And then it loops all the way through. And when it gets to the end, it'll see if it found another minimum along the way. Minimum, well, on that first pass, once it gets to the end of that array, it's gonna say, okay, the minimum's 2, which actually it's gonna remember the index. So 0, 1, 2, 3. So minimum equals 0. And then our minimum's at the 3rd index, so then we swap. I'll just write ARR, swap ARR and 0. Element 0 and element 3. So once we find the smallest one, put it at the beginning, and then keep repeating that until we have everything in order. Those 3 are fairly easy to implement. 2 that are much better. I'll just sort of do a quick picture on these. A quick sort is a good example of one of the more complex algorithms. But the name kind of implies what it does. So it's very quick, no matter how big our data size is. So we have some array or list or whatever our collection is, 27, 3, 38, 41, 2, 19. So we take our first element and call that the pivot. So that's our pivot point. And then we walk through this one in opposite directions. So on all of these, well, including the bubble sort, I didn't draw a picture there, but we'll start at the beginning and walk to the end. On this one, we keep track of 2 things. We have our low value and our high value. And what we do is we move our low value up until it finds something bigger than the pivot. So 9, that's smaller than the pivot. Our low value moves up, checks the 4. And in this case, up to the 27 there, which that's bigger than the pivot. So it'll stop moving there. And at the same time, our high value needs to go the other way. It's like the other side of the pivot. So it goes down until it finds something smaller than the pivot. So in this case, it walk one spot over and be like, okay, that should be on the other side of the pivot. And then those 2 get swapped. And then that continues until we have everything split nicely in half. for each half of that pivot element. And then there's smaller lists to sort. So then we do that recursively for the half size list. And again, for each half, and then do that on smaller and smaller lists where we just choose that middle element and get those in order. And it usually doesn't take but a couple passes. It's really, really quick on any size data set. A merge sort is probably another good one for the example for the board here. And then, yeah, that's kind of what I was thinking. I was going to run out of room around there. I'll pull up a list of this, because like I said, a number of computer scientists spent their entire working careers researching good ways to sort the data. So there's lots and lots of them. I just picked 5 to put on the board. This one's not bad to implement, but it does take a lot of code. It's you can see we just have a couple loops going and we walk in different directions. One goes up, one goes down, and they're doing different things the whole time, comparing to whatever this element is, and we split to each half of that. And actually, after we do that once, any of our other sorting algorithms are faster. So a lot of people, instead of doing that complicated thing recursively, they do it once, and then any other sorting algorithm we know about is faster after we divide it in half, because we have one list, but it's nicely organized that the small stuff is up at the front and the big stuff's at the end, even if it's not exactly in order, so it makes everything else faster. A merge sort's a little bit different. I wrote a really big example here. I'm going to cut that down. Well, 5, 72, 32, 21, 58, 7, 23, 38, 2, and 64. So a merge sort keeps cutting this down, just getting a smaller and smaller list. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 things. So this would cut it in half, and we'd have 2 lists with 5 elements each. Or really, this is for something much bigger than a list with 10 elements. But then we take each one of those lists. I'll just write out the one on the side here: 32, 21, 58. And cut that in half. Well, it's an odd number, so we would take that middle one and put that in a list by itself, and then turn the other ones into lists with 2 elements in this case. But eventually we would get down to where we have a whole bunch of lists with only 1 or 2 elements each. The one element just to take care of any odd numbers that might creep in along the way that happens to be there. But obviously a list with 1 element is already sorted, and a list with 2 elements is really easy to sort. So then we sort those and put them back together. That's the standard picture for it, and the standard terminology for describing it. And talking about that is probably seemed really weird when I just said that. It is a very, very quick algorithm, and talking about it, it sounds weird when we put it in English, but the coding for it's not that bad. It's a little complicated, so it would stretch out to a full class period. But that's kind of talking about and explaining it, because again, it's back to the why that sounded so weird when I said it in English. And I guess actually a better way to state that is it sounds so weird in English because that's one of those things that's much, much better for the machine, and machines don't work and don't process in the same way humans think. So when we actually describe stuff accurately for how it works in the machine, it seems to not make a lick of sense in English. But that was not bad to implement, but I chose some easy ones to go with for our class example. So first off, with bubble sort, which Yeah, I guess I didn't draw a picture there. Might as well draw a picture. So I can do it with a small one. 7, 12, or 13, a 2, 4. That's probably good. Bubble sort checks things one at a time. It's the easiest to implement. We just do 2 loops. Our first loop is looking at that, and our second loop just walks through the rest of it. I guess I could have done this. So I and J are the normal index values. I for index and J for the letter in the alphabet after that. And then just compares those. So 7 and 13, 7 smaller, then it move on up. And the J value would look at the 2. Oh, those are different, so we need to swap those. 2, 13, 7, 4. And then it's going to keep walking through there and goes all the way through. There's a lot of overhead there. So that looks good. So then our outer loop moves up to the second one. So it's looking at a 13, a 7. Oh, those need swapped. So it would swap those because 2, 7, 13, 4. Now it's looking at the second element. Sorry, I ran out of room. So it's looking at the 7, and our other index is comparing it to a 4 now, so we need to swap that. 2, 4, 13, 7. Moving along. So you can see that the smaller elements kind of, wherever they start at, they bubble up to the front. And then after a few passes, a few swaps, our second smallest element bubbles up to the front of the list and so on. So there's lots of overhead, but that's an easy one to implement. So when we have, really the reason for this is the categorical things, kind of like we saw with the stacks. And what was the other one we did a specific example for? A linked list, yeah. Almost said it anyway. When we saw the specific examples on linked list and stacks where we just added a couple lines of code into the class we needed for a particular topic, and straight in that object and turn our data type itself into a list. We might have some strange categories we need to sort by that the computer's not going to be able to handle that increasing numerical order, right? So we'd kind of work these in somewhere else. And bubble sort is definitely the easiest one to implement. So let's look at a couple of these and kind of see 2 examples. It's an active subject we learn by doing. So as always, following along an example seems to make the most sense in my mind for teaching this subject. Well, there's some stuff we have to talk about, but so we want to understand what's going on. That way we can take it to another programming language and we don't get stuck only able to do this in Python. Or, right, the name of this course is Software Development with Python. We're studying software development. Python is just the tool we're using to study that. We want to be able to apply it at the concept elsewhere. So what is my example doing so slow? Well, I'll make up some sort of list and I'll talk about this here in a moment. I'm going to call this stuff 1. I'm going to, for all 3 different algorithms we do, I'm going to make an exact copy of that list. But one thing that I guess is kind of relevant here. Whenever we have a list isn't holding the data itself. The list is a collection of references. Let me draw a picture and just talk about some explaining things. And it's important for our example. So it's okay if I erase this first side of the board. Just nothing there except the introduction to the list. topic for this evening. Well, that marker doesn't want to erase at all. So we've seen the stack heap diagrams, the standard way to refer to stuff. And if we have a variable, that usually points at a particular piece of data. All the ones and zeros in there, right? 0, 1, 1, 1, 0, 0, 1, 0. Whatever our data is, that's pointing at it directly. Whenever we have an array, we often represent it the same way, right? We'll come over here and we might draw a bigger box, but these are reference values. These are our named locations in memory, the things that are useful for a human to work with. What's really going on here is that list, the thing we call a list, actually just created another one of these. It just created a whole bunch of reference structures that are nice for a human to work with, but they aren't the actual data themselves. So it's more like, yeah, I'll draw it like, it's more like pointing at a small subset of a stack heap diagram. And in there is the stack with some indexing. And those are references to other data points. Those are the references to the data values. If that makes sense. So hopefully that yeah, hopefully two things happen there. You can see why we don't draw that picture, and when we want to generalize things in the stack heap diagram, we usually just do an extension of the acting like the list or the array is pointing at the data itself, but the list or array is actually pointing at a collection of reference values, and then those point at the data. And that's important because if we pass this into a method now, so somewhere else in our stack, we have this sort method that takes in an array. Well, when we pass this up, that is just a bunch of references. If you remember earlier in the semester, I used the phrase pass by value at some point. Drew a stack heap diagram and showed that whenever usually when Python passes data into a method, it makes a copy of that data. So we make a copy of the data, and that's what gets passed in. But when we need to pass in an entire list or array or dictionary or pass in an entire collection, that's actually a whole bunch of reference values itself. So we don't have any option but to pass by reference, which means if we make any changes in the method, they're going to carry through to the actual data itself, not just a copy of it. As a result, if we want to compare the exact same data, like we do this evening, as we do these three different algorithms, we'll have to make an exact copy of that data. So I just made up, whoops. Gotta be careful not to bump that thing. So just making up some data here. So like 1 or 13, 1, 82, 7, 19, 54, 2, 4, 9, 3. That'll probably work. Give us a few things. That'll give us a start. And then for each one of our algorithms, we'll just make an exact copy of it. And we'll start with the bubble sort. That's the easiest one to create. And we'll pass in an array. And I just talked about this return pass by reference. So if we make a change here, it automatically changes. I'll go ahead and I'm going to go ahead and put a return at the end so that we can just throw this right in a print statement, kind of minimize stuff. But a bubble sort is really easy. We just need two nested loops that walk all the way through our array for I in range 0 to the length of the array, but we don't have to walk all the way through both times. Okay. Our outer loop starts here and the inner loop compares to everything after it. So the outer loop does not need to reach our last element, right? Because there's nothing after it to compare. So our outer loop can stop at the length of the array -1. So, and remember, if you're in a place where it sets up the numbers that includes the last one, we would back that off even one more because we don't need our outer loop to go all the way through, basically. And the inner loop, likewise, doesn't have to start at the beginning. So, well, we always want to start one after where our thing is, but the inner loop, we do want to go all the way to the end. So the length of the array. And then all we have to do is swap it. I'm going to do this the general way. So if element I, that's our outer loop, so that's the one closer to the beginning. So that's going to look at the beginning. So if we find a smaller thing, that needs to come back to the beginning. So if that's bigger than the element from our element J from our nested loop, that's the one inside comparing that outer loop to everything else. Then we need to swap them. And I'm going to write that the traditional way of doing that. Right, the 3 cups. If we need to switch, if we have 2 cups both filled with a drink, and we want to swap what they're in. Right? Most people have some experience with children. Right? You're feeding a couple 3-year-olds their afternoon snack or something. You can accidentally give them the wrong cups, and they demand that the cups be switched. But both drinks are full. We need a 3rd cup to put that in. Right? We can take the drink from the first one, pour it in this empty cup. Then the 2nd cup pours into the 1st cup, and then that extra cup pours into the 2nd cup. So we need a 3rd thing to swap them. That's the traditional way to do it in programming. There's an easier way in Python. So whatever's in index I goes into the temporary thing. Whatever's in index J goes to a temporary thing. Or J goes into I, and then that temporary thing goes into J. In Python, since we can do multiple assignments at once, we can do that in one line of code. Right? Array I, array J is going to be reassigned array J, comma, array I, which actually handles that as a tuple. But whenever we do the multiple assignment thing with comma separated lists, the tuple part is automatically handled in the background. So we could write the parentheses, but if we leave the parentheses off, the interpreter will put them in for the multiple assignment things. Or a lot of people like to put them in on at least one side because it starts to look really, really strange. Say, okay, we have a tuple of those elements and we're just going to switch the order. That's a Python trick, so I figured I'd do it the normal way. Otherwise, I wanted to make sure and show you all that because it does make swapping things a whole lot easier, but not that it's hard to swap things. That'll be good. And that's it. That's all it takes to sort this. I'll come down. Whoops. And set up the guard. If the name is equal to main, we've seen that a few times, then print bubble sort. Print stuff one. Oh, I'm going to add a return so you can just print this directly. Return AR. Print bubble with stuff. We just talked about how we're passing by references with arrays and lists. So it would look exactly the same, but when I was putting the example together, since the whole point of this one is a classroom example, I thought it simplified it a little bit better, just throwing that return statement in so we can clearly see what we're printing. But I'll go ahead and print it afterwards as well. But yeah, the main thing, I just thought it exemplified it. It made it a little bit clear when we're printing which part, a little bit more clear. So save that and documents, delete. Class sort example. It's a good name for it. And we can give it a run. And you see that it printed that out fairly quickly, but how well did it do that? Let's add a counter in here. Bubble swap counter starts at 0. And every time we do a swap, we'll increment our counter by 1 and then print that out. Print number of bubble swaps is bubble swap counter. Oh, and you can see there at the end that on that very last line where we printed the stuff array again, our original list has been sorted, even though we just passed it in as an argument and didn't really assign it. Because, well, a list is a collection of is actually a collection of references, and the references point to the data values. So those only pass by reference. Unlike most of our stuff in Python that passes by value. So I had just a couple line breaks to get that ready for the next section. So we can see it took 26 swaps to do that. How many elements did we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 26 swaps to do 10 things. What if we had some more stuff here? 18, 3, 18, there's already a 3 in there. 11, 92, 44, and 38. How much is that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So if we go from 10 to 15, we went from 26 operations to 41 operations. And that would be a big part of the calculation on the big O, that measure of efficiency in our worst case scenario. clearly we are not in the worst case scenario, so it's not really the big O calculation there. But that's what we would do, right? We increased our input by 5, and the effect was that it took 15 more swaps to get those 5 more elements in order. So that's what the big O measurement sort of thing is. That's the easiest one to implement. You see, it takes very little thought. Just there's a counter took almost as much as the algorithm itself, right? A nested loops, when you get the inner loop compares everything else in the array to the outer loop. So what's another good one? I'll do insertion next. Oh, wait, is that how we're gonna work? Yeah, unboarded insertion. So let's do insertion. And that wasn't an arbitrary choice. Insertion and bubble swap are about the same efficiency. We don't really gain anything significant by doing this. Every once in a while, it might be a little quicker, but we're going to run it on the same data set, so we'll probably get the same number of swaps. So I'll set that up first. Insertion swap counter starts at emptiness. And here we look at our first element and walk through and try to make sure everything's in order. So once again, we'll have a loop that walks through everything for I in range 1 to length of the array. Which that might seem a little strange. This button. Said we're going to loop through, but we didn't start here. We started here because of the way this algorithm goes. It always has to back off one. We're always trying to make more space, right? If we find something out of order, we're going to squeeze it in where it goes. So as we loop through, our loop is actually one ahead of where we want. That way we can open up an empty space if we need it. If something needs to go to the very beginning and we started at 0, we can't open up an empty space before 0. But if we start at 1 and then we can open up an empty space before 1. But it's the reason for doing that. So you can see that's the main trick on getting the insertion algorithm to work, is remembering to not to start at the beginning, because we might need to open up a space to put something. So, oops, I was just typing somewhere and I have no idea where I was typing. The cursor wasn't where I thought it was, but I don't see any extra letters show up. I suppose the interpreter will tell me if there's a typo somewhere. So we set our key, the one we want to compare everything to, against that loop. And then we set up another index, only this time it is 1 less than the index from our loop. So that's the value we're actually looking at, so that we can pop open a space in the array before the spot we're at. And I like to do it with a while loop. So while that index is bigger than 0, which is another important thing, we have to specifically make sure that we don't get to negative indexes, which wouldn't cause a problem in Python, but it would certainly mess up our sorting algorithm, because the negative index in Python wouldn't crash. It would just go to the end of the list and start pulling from there. But while it's bigger than 0, let me spread that out for clarity. And our key is smaller than the one we're looking at. Then our next element becomes this element, the current one, and our index decreases by 1. I'll just pause so you can look at that code for a second. Kind of a mouthful. That one was the picture looked a whole lot easier on that, right? You start thinking about that algorithm, it's like, and it seems like every other line in that algorithm was a tricky thing, was a tricky step to have thought of. And yeah, it kind of is. People have spent a long time thinking about this. I forgot the word in. Then once we have that, well, that's our swap. So then we'll do our insertion swap counter increments. You know what? I'll put the counter in afterwards so we can see just the algorithm itself. So there's our swap, and then our J plus 1 element becomes the new key. So that one looks a little strange. We don't start at the beginning of our loop. That way we can step back and open a space before the one we're worried about. And then we kind of go through and compare everything to the one we're looking at, making sure our index doesn't go backwards too far. We don't want to go back before 0. So in this example, we start at index 1, so our key is a 3, and then our the J minus 1 index would be a 1. So our J, which is the I minus 1 index, would be a 1. So we compare 3 and 1. The key is not smaller than the array, so we can keep. So we just come back around. Our i's can increment. So now our key is a 7, and our key is our key is the 7, and the J index is looking at the 2. So 7 compared to index 2, or sorry, the second element, index 1, that's still in order. So the key of 3 is smaller than the 7. Oh, wait. No, the key of 7 is not smaller than the comparison of 3. So it keeps going. Comes back around. The key is 5. Looks at the one before it. It's a 7. So, well, I and J are both bigger than 0. So the first part of the condition is met. But when we compare the key to the Jth element, they're out of order. So now we're like, oh, that's wrong. So those swap. 7 swaps with 5. 5 is still the key. So we come back around and J goes down. So now we compare 5 and 3. Well, those are good. So it'll stop moving there. But it would walk all the way back down to the beginning of the array, finding where that thing went. So you can see that sorting stuff isn't always a straightforward process. Now I guess I need to call that one. Print insertion. Print stuff 2, which doesn't exist yet. I have to go make a copy of our original data. And then we'll print the insertion sort with stuff 2 passed in. Or stuff 2 doesn't exist yet, so I have to go create that. So I'm just going to copy the original data using home and in keys, like always. Makes that a whole lot easier to copy a whole line. And well, we'll do 3 of them, so I might as well make stuff 3. And yeah, then after we do the third one, we'll pass strings through this. We'll make a sentence and pass strings through there the same way. But that's kind of trivial examples. So you can see it sorted it. There's our insertion sort. Everything's in order after doing it. And you can see up here in the variable explorer on my screen, at least, that the original list is stored. There's no need to return sorting a list. I just did that because when I was getting the example ready, I thought this line made it a lot, help with the clarity on what we were doing. Help with clarity of the example. So let's see how many that took. So again, we need an insertion swap counter starts at 0. That's a big word to do. So I'm gonna come down here. And every pass through our array, we do it. That while loop is what does the swapping. And I'll copy the print statement from the one earlier. Number of insertion swaps is the insertion swap counter. Oh, let me finish out that line. Actually do something with that variable, increment it by 1 so that our counter has a reasonable number afterwards. I'm going to close that. The effect I was going for was really clearing out the variable explorer, so it would have been exactly the same. So you can see we got the same efficiency as we did from the bubble sort. It didn't really improve anything. This one, as far as the thing about insertion sort is with the picture, that makes a lot of sense to a person. Let me throw some arbitrary print statements in here. Print, all right. So here I'll print 1 at every swap. So there's 41 swaps. And because of the way like geometric patterns start to form, you can kind of see that bubble stuff, right? Then the small elements are moving up to the beginning, and the other elements are moving down, sinking down to the end. And we get this sort of diagonal thing, diagonalization showing up. As our big elements, or as our single elements move forward, and the big elements move back. You can see a difference there. Or if I undo the level in there and just print once, on the oh, that's the same print. Let me undo that twice and print once for the outer loop. You can see that after each pass, by the time it gets back out to the outer loop, the thing is completely changed. So part of that checking how well things are working that we've been talking about some. Let me do that here. I'll print the array every time through that inner loop where our 41 swaps are happening. Kind of looks like there's still some nice patterns showing up. Oh, I guess one thing about the bubble sorts though is look, 13 started here and moved over here, then moved over here. It's getting further along, but then 13 has to come way back over to the beginning before it's in place. So things don't go directly to the spot they need to go in the bubble sort. Right? Or something near the beginning could inadvertently get swapped and left at the very end for a long time. And things get moved out. They don't move, only the one element moves towards the spot it needs to go. But with an insertion sort, you can see that 13 started at the beginning. Yeah, when it opened up that spot, notice we got an extra 13 in there. There's only 13 in our data set, but suddenly we have an extra number there. And then a 1 takes the place of one of them. The same thing over here. There's only 182 in our data set, but then we have 2 of them. And then suddenly we have 2 13s again. Then we'll have 113, still have 2 82s. As in that spot opens up, something has to be there. So we end up with that extra data along the way, which leads to some strange patterns. So you can see there's quite a bit of overhead in both of those. And what we saw from the counter, it took 42 swaps to do that. I'll move that print statement out one line. And you can see there's the original data. And then those duplicates are still showing up. Because that's what this extra line at the end is. That's fixing that. So I'll move the print statement after that. So here it is without the duplicates. And you can see that even though it's like 1's here, so that moves back pretty quickly. 7's here, so that stays about where it's at. The 2's, a lot of the stuff is staying in the position it was. It doesn't get moved to the back or the front until that index is turned to move. And with our bubble sort stuff gets swapped constantly. But here we can see that things are staying where they were until it's their turn to move. So they don't move inadvertently, but we still end up with the same number of swaps. The third one I was going to do is a little bit more efficient. I'm going to turn off that print statement. We don't need all those. So both of those took the same number of times to do that. I come up here and take out 5 elements, 1, 2, 3, 4, 5. Take out those 5 we added, and see it got back to the 26. So the 10 elements took 26 swaps to sort. So that's exactly what essentially the same number of operations as our bubble sort. Quite a bit different. One thing people like about this is, like in the picture, that's how humans would organize things, right? We think, okay, we need to put things in order, so let's look through, find the spot where it goes, and then stick it there. But we don't gain anything over the one that's just the easiest to implement. The next one does gain a little bit. So a selection sort, and pass in an array. And here we look at our minimum value and then walk all the way through to see if a different index is smaller. Oh, the camera wasn't pointing at that. Let me move the camera so the one over here was our selection sort. We assume the index 0 is the minimum, holds the minimum value. We go all the way through comparing everything. And when we get to the end, if we have a different minimum, we compare everything and then we hold keep track of the index that has the minimum value. So then when we get to the end, then whatever the minimum value is, we just move that to the front. So once again, we have to loop through in range of 0. Yeah, I jumped right ahead to the second loop. Our outer loop does the whole thing. We need to actually look for that minimum. So we have to go from beginning to end. So a normal outer loop through our array, and we'll start by assuming the minimum index is that that smallest one. And then after we take care of the first element, we'll assume the second index one, or the second element, is our smallest one. And we'll keep doing that until we get to the end. Then we do our inner loop. So for j in range, again, we don't need to start at 1 because we're doing this for comparison. So there's no need to compare to the exact same thing. We know those are always going to be equal if they were both would have started at 0. And then we'll loop all the way to the end. And if the one we're looking at is smaller than whatever our min index is, then we'll swap the min index. And yeah. Then after we get all the way to the end, after our inner loop goes all the way to the end of the array to make sure we have the smallest index, then we move that to the beginning. So temp equals what was the beginning, where we started our outer loop. Then the start becomes whatever we found the minimum index to be. And the one that did have our minimum index gets that temp value. So you can see we're back to that spot we were earlier, where we might send things out of order. Right? Maybe we have a 3 at the beginning and a 1 way over here in the array later. We send that 1 to the beginning, but then we send the 3 way back here, which means we have to, on the next pass, we have to go through and find that 3 and move it back to the beginning. So we still have quite a bit of overhead in this one. But that's the entire algorithm on that. Oops. Return ARR. Okay, I don't know why that threw an error the first time. So kind of a simple algorithm, really. It might not have been your first intuition to just clear the indexes like that, but a fairly easy one to code. And in this case, we usually get some improvements over those previous 2 that we looked at. So print out stuff 3, and then we'll use that selection sort on stuff 3. So right after that, we can see it sorted our data. Let me throw some print statements in here. Well, really, we only do the swap at the end of the pass, so there's only one place that we could really put the thing here. And when you look at that, you'll see that anything moved back in the wrong direction. So 113. Yeah, 13 moved too far over. 13 moved all the way past 19 and 82 and all sorts of stuff. So we have to move that back later. But well, you can see all the swaps right there. That's a much shorter list than the other one gave us wherever we put the print statement. So selection swap counter. It starts at 0. Then after we make a swap, yeah, I paused there for a second, trying to decide whether I should do that here or up here. The biggest advantage of this in general is that we're not, in most of our situations, we're not swapping integers. In this case, we happen to be swapping integers for both the index and our data. Why is my cursor doing that? There we go. In this case, when we swap an index like this, indexes are usually much smaller than the data we would be sorting. Right? We wouldn't be sorting a single element, we'd be sorting a multi-dimensional array that represents an entire row of a database. So the swap is usually lots of data, so that swapping an integer doesn't count for the one for our concern. In this case, swapping our data happens to be the same size as swapping an integer. But you can see for the same data set, we went from 41 swaps down to 15 swaps. Or if we take those 5 at the end off to do that comparison. 1, 2, 3, 4, 5. Cut. Run that again. So that's kind of interesting, isn't it? We had 10 elements, it took 10 swaps to get them in order with a selection swap. We put those 5 back in. 15 elements took us 15 swaps to get them in order. So a very, very different big O, right? It took going from 10 to 15 elements, went from 26 to 41. So 15 more steps for the 5 more elements. But so 3 steps for each element that we added. In this particular example, obviously in the actual calculation, we want to do that lots of time and get a bunch of averages. But in this case, we only took 1 more step for each element that we added. Okay, so not the exact calculation. The exact calculation would involve lots of averages and things, statistics taking over amount of time. But a quick version of our big O here makes it seem like those first 2, our big O was 3. It was big O with 3n, is 3 times as many, 3 steps for each one that we fed in. And then here, when we change that, when we increase the input, it was just a big O of n. The number of steps taken increased by the same number as our inputs. So that's what the big O measurement is. Everything is. And then obviously this would apply for other data types. Custom data types really, but I'll just do a string. Here is a collection of words that should work nicely to check out a sorting algorithm and compare it with others. Dot split. I get the thumbnails on one. Split on a space. So a big long sentence and dot split at the end. We've seen that before. Just a bunch of words. Here is a collection of words that should work nicely to check out a sorting algorithm and compare it with others. So quite a few words we can split up there. And then once again, probably want to copy all those. So home, shift in and copy, paste, paste, and we'll check each one of our algorithms again with stuff 4, 5, 0, and 6. I'll draw a line in there, so paste that, and we get stuff 4, 4, 5, 5, 6, 6. Oh, I was hoping to be done by 7:30. There's one more thing I want to look at, but I was just looking at a web page. So once again, you can see these two took the same amount. It took 101 swaps to get those words into order. Quite a few words there, so a lot of back and forth. And only 21 swaps to get that with the other algorithm. So the algorithms can make a big difference, right? These are small things. That was one sentence or just a small list of integers. And you can see how much the increase takes. So when we get up to huge data sets, the way that the data is sorted can make a big difference. And oh, it's already erased from the board. And if the sorting order is specific to our data type itself and not something we can generalize like ascending order for numbers or the alphabet, it has to be something very specific. And we kind of have to write our own sorting algorithms. And a lot of people have spent their entire working careers working on that. That's a big deal. And we saw there, if we have to double our size, and then if we add, so just for a starting point, we double the size of elements we have, and then if we need any changes, it takes 3 times as many as we added. It's 3 times as many as the inputs we added, more steps. So if we're up in the hundreds of millions of data sets, that's a lot of steps in processing. So finish out here, the site Geeks for Geeks, they have really great tutorials. Hopefully you all have stumbled across them by now. They're usually at the top of the search results. They stay on top of things better than others. They'll show you ads like crazy. But if you just search for sorting algorithms, they have a breakdown on them. And you can see there's a lot of them here. So selection sort, bubble sort, we saw those. And insertion. Same thing with recursion. Merge sorts, that's one of the ones, that's a very popular one I put up there. Heap sorting. They have a nice little picture showing what a heap is, and we have our data and hash values for the data, and structure it like a tree. And here's where we get to the Python example of it. We start scrolling, and we hit another function that's necessary. So that one takes 2 functions and quite a few lines of code for it. But if you check, just Google sorting algorithms, you'll see a whole bunch of them here. Sort is really fast. But you'll see if I start scrolling, there's an awful lot of code there. There's where we get down to calling it. We'll start scrolling back up. There's an awful lot of code and several functions involved in that. So kind of a big deal to get that one going. I'll leave that to you to kind of check on some of these. Pigeonhole is a neat one. What's the way to summarize pigeonhole? Pigeonhole is like squeezing something into place. It's the generic type of it is the best place to store a pigeon is in a hole that is big enough to fit a pigeon in. So start shoving pigeons in holes. Eventually, you're going to find a hole that's the perfect size for the pigeon you're looking for a holding place for. Is the basic idea of it, but a lot of code. Well, not a lot of code, but it's kind of some. We use extra arrays in order to find the perfect order for our array. Cartesian tree sorting. This one a little more. So you can see our picture doesn't even. Our picture has to have multiple shapes in it there, and extra pictures to describe what's going on in the picture. And it takes its own data type that we pass our other data into, and scroll and scroll and scroll. There's a lot of comments explaining that, but there's an awful lot of code in some of these. But usually the ones that have an awful lot of code means they're going to be very, very quick sorting algorithms, right? Sort of thing where we can feed in 2 billion data points and not have to wait till tomorrow to get our results. I'll leave that for you. Search. Geeks for Geeks has nice explanations on a lot of them. Just Google sorting algorithms, you know, see those. There's lots of them. It's a big deal. Obviously, we have the dot sort thing, but it's that if we have, you know, our list dot sort that's built into the array or built into the language, that is restricted. There's only that has to be completely generalized to handle every situation. So especially when we don't have a normal order that our stuff's going to go into, we have to specifically define how to sort it. So a very big deal. Geeks for Geeks is a really good site. Hopefully, it's always at the top of the Google results, so you probably stumbled across that along the way searching for things. But they have an excellent breakdown on lots and lots and lots of sorting algorithms. Show them in multiple languages, including Python, so you can check there and see some different ones. Otherwise, I just wanted to look at a couple of them, talk about some others, and you see it and express that it is a really big deal. Yes, every one of our languages, the built-in arrays and lists and things do have a dot sort method with parameters we can fill in, but that is a minimally acceptable sort, a minimally acceptable type of sorting. That's like the bare minimum. It gets it in order, but it's if we have specific needs, that generic one's almost never going to cut it for us. So kind of a big deal. Just introducing it here. Does anybody have any questions about those? Okay, question about the module 5 assignment or module 6 assignment, so we can take a look at it. I'm gonna go ahead and stop the video though and call it an evening. So y'all have a great night. Gonna go over the module 6 assignment if you want to stick around for that. Otherwise, I will see you all on Thursday.